Okay, welcome, and this is the last video for the review session. So after this, it's going to start in chapter 1. So this is all of the last bit of review material that you'll need to know for this semester. Okay, so and this is all about radical expressions. Okay, so radical expressions are algebraic expressions that involve radical signs. Okay, so again, the notation is very simple, and most, if not all of you, are familiar with it. So this is the radical expression. The number or the expression under the radical is called the radicand. The radical symbol, obviously, you should be familiar with. And then the n is called the index, or the nth root of a is the index. So now we've seen how we can, by definition, write a root in this way. So we're familiar with the last session with rational exponents, that this can be written as an nth root because they're the same thing. So any exponential of this type can be written as a root. So the nth root of a is the same as a raised to the 1 over nth power. Okay, so you can write it in as a root notation, or you can write it in exponential notation. So radical notation, again, this is something we were introduced to last section, can be rewritten using this new notation. So now, if we look at this, we can write a to the m over n power as the nth root raised to the mth power. Or we can bring it inside the radical. So either way, it's okay. Okay, remember, we've seen this before. We can exchange these, and it's the same way. You'll get the same answer. Now, we use the familiar notation root a for the second root. So if there's no index, it's assumed to be 2 for the square root. For even values, n, so for square roots, fourth roots, and so on, when a is positive, there are always 2 nth roots. So it's a plus or minus. Okay, so if the root is even, there's going to be 2 roots, a plus and a minus. So there's the principal nth root. So whenever we talk about the principal nth root, it's always the positive root. And then we have the negative root. So if n is even, we always have 2. We have the principal root and then the negative root. Okay? Okay, so for example, it says write each root using exponents and evaluate. So we can use this as 16. So the fourth root is 16. Well, we can write 16 as what? 2 to the 4th power. And then we can rewrite this as 2 to the 4th power to the 1/4 power. Okay, so as follows. So 16 to the 1/4 power is going to equal 2, because 16 is 2 to the 4th, and like we saw in the last section, it cancels out with the 1/4 and gives us 2. And then similarly, we could take the negative of this, which again, the negative sign is outside the root. So we can handle this separately and then carry the negative sign with it. So we're going, in this case, we're going to get -2. And so if we look at part C here, we've got -32. Now, we look at the root, and remember from the last section, this is an odd root. Okay, so in this case here, the negative sign does not pose any problem because it's an odd root. So we can raise this to the 5th power. So this would be -2 to the 5th power, and that's going to cancel with the nth root. So the 5th power cancels with the 5th root, and so we're going to get -2 as our answer. Voila. Okay. And then likewise here, 1,000 can be written as 10 to the third power, and the third power cancels with the third root, and so we're going to end up getting 10 out. And then again, in this case here, we can write 64 as what? 2 to the 6th power, or excuse me, I'm sorry. Let me see here. Yeah, this would be 2 to the 6th power, and 729 is going to be 3 to the 6th power. And so we can write this as 2/3 raised to the 6th power, and then of course the 6th power cancels with the 6th root, and so we get 2/3. And then here, there is no answer, because this is an even root, and we cannot take an even root of a negative number. And so there is no real number that will give us the 4th root. Okay, so now converting from rational exponents to radicals. So it says write in radical form and simplify. So we're going to take all these and write them now in radical form and then simplify going from there. Okay, so if we look at 8 to the 3rd power, let's write this in root form. So the 1/3 we can write as a 3rd root. So this is going to be the 3rd root of 8 squared. Okay, so we can write it this way. And so again, we can take the 3rd root of 8, which is 2, and then we get 2 squared, which is 4. And then similarly, since this is an odd root, we could take the 5th root of negative 32 and then take it to the 4th power. Well, the 5th negative root, the fifth root of negative 32 is negative 2. And then negative 2 to the 4th power is going to give us positive 16. Okay? And then C, now again, the negative sign is outside this, okay, because there's no parentheses. See here, the difference is there's parentheses here. So there's no parentheses, so we treat the negative sign as outside this whole thing. So we treat it separately. So now in this case, we're going to take 16 to the 4th power and then cube it. So the 4th root of 16 is 2. And then 2 cubed is 8, so we're going to get a negative 8. Okay? And then x to the 5/6, we're going to write this as a radical form, but we're not going to be able to really simplify it any further than that. So this would be the 6th root of x raised to the 5th power. And so this is the way we would keep it. Okay. Similarly, this here, now the 3 is outside this, so we treat the 3 separately. So it would be the 3rd root of x squared. So it's going to be 3 times. So 3 comes outside, so 3 times the 3rd root of x squared. And then f would be 2 times the square root of p. So it would be just 2 times the square root of p, which should just be this. And this here, since now this is in parentheses, it's going to be the 4th root of the entire thing. So that's just going to be written as this. And we're done. Okay. Now, again, caution. Got to be careful here. Okay, so now it is not possible to distribute exponents over a sum. So this is the same similar thing that we saw with rational exponents. It's the same thing. So you cannot distribute the radical across sums and differences. Okay, so do not mistake this as being the same as this. It's not. Okay, you cannot take the nth root of this plus the nth root of this separately. Does not work that way. Okay, and it's easy to see if you just use an example. So now, Let's look at these examples. Converting from radicals to rational exponents. So now here, we're going to go the other direction. We're going to write this as x to the 5/4 power. Okay? This would be the square root of 3, so it would be 3 to the 1/2, or it would be just the quantity 3y quantity to the 1/2 power. Excuse me. So now for C here, 10 is outside of this, so 10 is going to be left alone, and this is going to become z to the 2/5 power. So it's just going to be 10 times z to the 2/5 power. Okay, and again, so here again 5 is outside the radical, so it's just a multiplication, and so this is going to be 2x to the 4th raised to the 7/3 power. Okay, now, then we're going to distribute, and we're going to say, hey, this is 5 times 2 to the 7/3 power times 28, x to the 28/3 power. And then for this one here, we got this is just the quantity. So again, all we're going to be able to do is write this whole thing to the 1/2 power. So again, we can't distribute across the plus sign. So this is the best that we can do. This is the simplest form. So again, make sure you do these exercises for more practice. Let me know if you have any questions or if you get stuck, and we can work it out in class. Now, again, we can't simplify this expression to x for all real numbers x. Okay, be careful, because in this case here, x may represent -5. Okay, so if x represents -5, this is not the same as x, because if we square this, we get 25, and then the square root of 25 is 5, is not equal to x, because again, x is -5. Okay, so take care of the fact that a negative value of x can produce a positive result. Okay, so we use absolute value in this case. So for any real number a, the following holds: that the square root of a squared is equal to the absolute value of a. Because remember, a could be negative. Okay, so in this example here, -9 squared, and then you take the square root, is the absolute value of -9, which equals 9. And then, of course, +13 squared also equals 13. So it's going to be the absolute value of a. So again, when we deal with square roots, this is the definition that we're going to use for the square root of a squared. Okay? Now, in a lot of cases, we're dealing with positive numbers, so we tend to drop the absolute value signs. But again, be careful. It is there. So, evaluating the nth power of a to the n. So if n is even, this is the definition we have to use. If n is odd, then we drop the absolute values, because it doesn't matter. Okay? So in this example here, we have this. So this is an even root of p to the 4th. So we can write this as p squared quantity squared. And since this is an even root, we would take the absolute value of p squared. And so that would be the answer, is absolute value of p squared. Okay? Which is equal to p squared. Okay, why? Because this is always going to be positive, so we can drop the absolute value signs. Here, we have the 4th root, and again, in this case, it would be the absolute value of p to the, the absolute value of p, because it's the 4th root of p to the 4th, so in this case, it would be at the absolute value of p. In this case, we could not drop the absolute value signs because it's p to the odd power in this case. So p could be positive or negative. Now, in this case here, c, we have the square root of this expression. So we need to write this as to the power of 2. So this would be 4 squared. This would be m to the 4th power squared, quantity squared. And this would be r to the 3rd power, quantity squared. Okay? Okay, so now what we do is once we do that, we put the absolute value signs around it because it's an even root. But then we look at the inside and we look for, obviously, constants, if it's positive, are just going to be positive. So we can drop the absolute value for this one. This is even power, so it's always going to be positive, so we could drop the absolute value for this one. But this one is odd, so we're going to have to keep the absolute value symbols around this one. So that's how we get this final expression here. Okay, and this all begins with because we have an even root. Here we have an even root, so we're going to look at the same thing. Now look at this. This matches this, so this root cancels with this one. So again, we're going to keep the absolute value sign because we end up with a negative 2 here, which makes it a positive 2. Okay. Now, if we look at the next one, again, it's an odd root. So we don't need the absolute value sign. So this cancels with this, and we just end up with m. No need for the absolute value signs. Here, even root. So we're going to add the absolute values, even though it cancels. So it cancels with 2. The 2 here cancels with this 2 here. So we end up with the absolute value of this expression, and we have to keep the absolute value sign because there's no squares in here to cancel, and it's an addition, so we can't go across the addition anyway. Now, what about this one here? Same thing. We've got this case here. We want to see if we can factor this into a perfect square. Okay. Now, in this case, we can, because this is a square. This is a square, so this is 2 squared. This is x squared, so 2x, and this is double 2x. So this is a perfect square of x minus 2, quantity squared. So this will cancel with this square, and we have to have the absolute value signs because it's an even root. And so this is our final answer. Now note, when working with variable radicands, we will usually assume that all variables in the radicands represent only non-negative real values when we're working with variable radicands. Okay? The following rules for working with radicals are simply the power rules for exponents written in radical notation. So this is things that we've already seen. Okay? So this should not be a surprise. Okay? It should be intuitive from what we've already discussed. Okay? So make sure you know these. Make sure you memorize these. Okay? These are directly a result of what we've already studied under exponents, properties of exponents. Okay, so here. So in this case here, we have some more examples. We want to simplify, so again, assume all the variable expressions are positive real numbers. So again, we want to simplify this. So one way to simplify this is we want to write this in some form that we can combine these. Okay, so in this case here, we can combine these by using the property of radicals, and we could write this as one radical, and so we can write this under the radical, and we get the radical of 6 times 54, which gives us the square root of 324, which turns out to be 18. Here, we do the same thing. This is a cube root, and this is a cube root, so we can combine these under the same radical, and so we get the cube root of m times m squared, which gives us m cubed, which then cancels with the cube root, and we get m. And notice that we don't have to have the absolute value signs. And so our answer is m. Here, we get the square root of 7. And so we can use the fact that we can split these up into two radicals. So we can do the radical of 7, the square root of 7, divided by the square root of 64, which is a perfect square. So we can simplify this as the square root of 7 over 8. And we're done. Here, we can again do the same thing. We can split this up into the radical, the fourth root of a over the fourth root of b4. And this simplifies to b. Okay? And since we're assuming that this is a positive number, we can drop the absolute value sign here. So again, we're assuming that b is positive, so we don't need the absolute value signs. Here, again, we've got a radical within a radical here. And so that means we can multiply the indices. Okay? So that means we can multiply these and we get the 21st root of 2. And we're done. Here, we've got a square root, the fourth root of a square root. And again, we can multiply these and we get the 8th root of 3. And we're done. Okay? So again, here are some exercises you could do to practice. Again, all we're doing is applying these properties that we've introduced. Note, converting to radical exponents shows why these rules work. Again, these are directly a result of what we did using rational exponents. Okay, now simplified radicals. So here are the rules for dealing with simplified radicals. Okay, an expression with radicals is simplified when all of the following conditions are satisfied. The radicand has no factor raised to a power greater than or equal to the index. Okay, so you should have no powers under the radical that are equal to or bigger than the index. The radicand has no fractions. No denominator contains a radical. So that means you cannot have any radicals in the denominator. 4. Exponents in the radicand and the index of the radical have greatest common factor of 1. Okay? So it cannot have any common factor bigger than 1. All indicated operations have been performed if possible. So let's look at this example here. So let's simplify this radical. So we want to make sure that this has all of the steps that we've just went over. So let's look at this one. So we first factor this out and see if there's any factors that we can raise to a perfect square. Well, if you look, it has a factor of 25, which is a perfect square. So then we can split this up into two radicals. So the radical square root of 7 and the square root of 25, which simplifies to 5. So we end up with this, and this is in simplified form. We're done. Now, let's look at this one. Now we've got the fifth root of 32. Well, 32 can be written as a power of fifth power. So this is 2 to the fifth. So we can rewrite this as 2, which then gives us negative 3 times 2, which is negative 6. So this is simplified. Now let's look at this one. Let's simplify this by expanding it out into its factors of cubes. So 81 can be written as 27, which is a perfect cube, times 3, times x cubed, times 2 squared, times y to the 6th, which is also a multiple of 3, times y, times z to the 6th power. Now, we group all of the terms that is not a power of 3. So this here, these 3 can now be separated. So now we're going to split this up into 2 cube roots. Okay, so this is 3 cubed, x cubed, This is y squared cubed. This is z squared cubed. So all of this can be canceled with the cube root, and we get this. And the rest of it just stays as a cube root. And so this is our final expression. Okay? So again, there's nothing more that we can do with this. So try these exercises for more practice. Okay, now, so operations with radicals. Radicals with the same radicand and the same index, such as these two, are what we call like radicals. Okay? On the other hand, examples of unlike radicals are as follows. This and this are unlike radicals because they have different radicands. These two are unlike radicals because they have different indexes. Okay? So if they are like radicals, we can combine them, just like we would with like terms when we deal with polynomials. Okay? So if we look at these under example 7, because these have the same radicand and the same index, we can combine these by the operation of subtraction. Okay? So what we could do is we could factor out these like radicands, and we can subtract the 3 and the 7. So we get 3 minus 7 times the like radicand. So again, so we can factor out this like radicand, and we get negative 4 times this expression, and we're done. Similarly, if we look at this, we have 98x cubed y plus 3x times the square root of 32xy. Okay, now, the thing is what can we do with this? Well, if we factor out a 4 here, okay, well, we want to see if we can figure out a way of getting something that gives us a 32xy here. Okay? And a factor of 4 will do it, I believe. Let me see here. 4. No, 4 will not do it. Okay, so so in this case here, if we factor this out, what are the different prime factors? Well, here we get 49 times 2. Okay, so if we factor this out, okay, so we get 49 times 2 times x squared times x times y. And this gives us a 3x, and this gives us 16 times 2 x times y. Okay, so there's a perfect square here. Okay, and there's a perfect square here. And look, now we've got something that looks the same. So this can be pulled out, this can be pulled out, and this can be pulled out. So what happens when we simplify them individually? Okay, even though there's not something here that's perfect, we can still see if we could simplify this. So this simplifies the 7x times this. This gives us 3x times 4 times this. And look, now we have a common radical. So now we could factor out this common radical, and now we've got this. And so now we can combine like terms here, and we get what? We get 19x times this, and we're done, because we can't simplify it any further. Okay, now what about this one? So again, we have like indices. Okay, so again, we're going to try to simplify each of these. So this here is the same as 4 cubed. Okay. So 64 is the same as 4 cubed. This can be written as m cubed n cubed times this. Okay. So again, I'm not going to explain this. You should see this how to do this based on previous videos. And so now this cancels with the third index and gives us this. And we're left with this radical here. And likewise, we can write this. This is a perfect cube. And we can cancel with this third root to get this. And we're left with this. And notice that we've got like radical. And so now we can use the distributive property again to factor out the like radical. And we get this. Now, in this case here, we can't simplify this any further. So we would have to leave it in this form. Okay, and again, here are some exercises you can use to practice. Now, again, be careful with this. Oops, hold on. In this case here, this term and this term in 7c are rewritten in the final form using the distributive property. Okay, so again, notice, oops, hold on. Come on. Right here. Okay, so just be careful. We use the distributive property. Okay, when we use this and this in example 7c. So just be careful. Again, these are common mistakes that students make. So again, just be careful of that you don't make mistakes where you can avoid them. Okay, now let's consider these. So we're going to simplify each of the radicals, and we're going to assume that all of the variables are positive real numbers. So we're going to avoid the absolute value sign again. So again, keep in mind, in general, you've got to use absolute value signs when necessary. So now in this case here, we're dealing with a constant, so it's already positive, so we don't have to worry about that. So here, how would we simplify this? Well, we would take this and write it as a rational exponent. So this would be written as 3 to the 2/6 power, which would have been simplified to 3 to the 1/3 power, which is equal to the third root of 3, and we're done. Okay, now if we look at b here, we've got the 6th root. So we want to find a way to write this as simplify this. So we're going to write this as exponential form. So we're going to write it as 1/6 power. And then we're going to distribute the 1/6. Okay, so we're going to have x to the 12/6. And so now we can simplify both of these. Okay, so again, we want these exponents in simplest terms, right? These fractions in lowest terms. So this is going to reduce to eliminating the common a common factor. This is going to be reduced to 4/2, or excuse me, I'm sorry, 2, because we can reduce 4/2 even further. Okay, so we can divide this by 6. This is going to reduce to 1/2. Okay, so now we can change it back into radical. So this is going to be x squared to the square root of y, because typically we don't want fractional exponents. We want to have things in radical form. And then here, we're going to use, again, our exponential form to rewrite these. So we get 9 here. Okay, this is the square root of 3, so we're going to write this as 6 to the 3/2. And then we're going to write this as 1/9. So look at this. We have a power raised to a power, so we can use the power rule. And so we get 3/2 times 1/9, which gives us 3/18, which reduces to 1/6. And then we can rewrite this in radical form, and we're done. Okay, this cannot be simplified any further. Okay, now in part A, we simplified this as the cube root of 3. However, what about this? In order to simplify this, okay, the variable x must represent a non-negative number. Okay, because we have an even root. Okay, so for example, consider the statement given by this. Okay, we have -8 to the 2/6 power. Okay, so this is negative 8 to the 1/6 power squared, which is basically the same form as this, right? Now, this is where we get into trouble because look at this. This is a negative number, and we're trying to take an even root. We can't do that. Okay, does not result of a real number. Okay, so we can't solve this because there's no real number that will give it to us. Okay, now on the other hand, if we do it 1/3, right? Because this reduces to 1/3, right? Negative 8 to the 1/3 power we know is negative 2. We don't have any problem with the odd root. Okay, so here, even though 2/6 is equal to 1/3, we cannot make that equation. So again, so you got to be careful here. This here, even though it simplifies to the cube root of 3, okay, we cannot simplify the general case of x unless x is a positive, or excuse me, a non-negative real number. Okay, and this example shows you why. Okay, so even though it works in this specific case, it does not work in general unless x is a non-negative real number. So just be careful with that. Okay. Okay, so now if a is non-negative, then it's always true that this is going to be the case. Okay, and then we can simplify it with no problem. Okay. Okay, so let's look at these. So we're going to find each product. Now, here we're going to use the FOIL method, right? So we're going to multiply this by this, which is going to give us what? Just use the FOIL method. This is going to give us the square root of 7 squared. Well, this is positive, so this is going to cancel each other out, so we get 7. Well, what happens here? Well, this is what? Plus and minus. So this is, if you want to look at it, x minus y times x plus y. So this is going to have that form that's going to give us the difference of two squares. So it's going to be the square root of 7 squared minus the square root of 10 squared, which is going to cancel each other out. So we get 7 minus 10, which is negative 3. Okay? Now, here, we can't do that because this is not of the same form. So we're going to have to use the FOIL method here. So this is going to be this is going to be the square root of 2 times the square root of 8. So that's going to be the first. And then it's going to be the outside ones. So we're going to get negative 5 times the square root of 2. And then we're going to do the inside ones, which is going to give us this term. And then we're going to do the last ones, which is going to give us this term. So then what we're going to do is now we're going to simplify using the rules of radicals that we learned. And this is going to be the square root of 16, which gives us 4. This is not going to be able to be simplified other than putting the constant in front, which gives us this. This gives us this, which again, this we can simplify because this is 2 times 4. And so we can split this up in 2 times the square root of 2. So this simplifies to this. And then, of course, this is going to give us minus 15. And then, of course, this is going to simplify to 6 root 2. And now we can simplify this because it has like radicals. And this is like terms, combining like terms. And so we get negative 11 plus the square root of 2, and we're done. Okay, now go ahead and try these two exercises for practice. Okay, now, rationalizing the denominator. So what happens, remember the rules. We can't have radicals in the denominator. So what do you do when you do have radicals in the denominator? This is where we're going to rationalize the denominator by multiplying the top and the bottom of the fraction by whatever radical is in the denominator. So for a, we're going to multiply the top and the bottom by the root 3. And what's going to happen is that's going to get rid of the radical in the denominator. And so that's going to give us 3. And we end up with 4 root 3 divided by 3, and we're done. Okay, so now this is going to be our final answer. So whenever we end up with a root in the denominator, we're going to use this technique called rationalizing the denominator to get rid of it. And so this would be the correct answer. So if you left it like this would not be correct. You would have to go to the extra step of doing this. Okay. Now here in part B, we have a rational expression under the radical, and so we're going to have to first use the property of splitting it up, okay, using the quotient rule. And then the one in the top we don't care about. We would leave it that way. But the one in the bottom we would have to get rid of. So we're going to have to multiply the top and the bottom by the 4th root of 5. Okay, now here's the thing. The denominator will be a rational number if it is equal to this. Okay, so the denominator will be a rational number if it equals this. That is, 4 factors of 5 are needed under the radical. Okay, so we're going to multiply by this. Okay, so here's the thing. We've got 5 here to the first power. And because this has only one factor of 5, 3 additional factors are needed. And so we're going to multiply the top and the bottom by this. And you'll see why. Watch what happens here. So now when we multiply the top and the bottom by this expression, watch what happens here. This becomes 4 5 to the 4th power, right? Because we've got 5 here. If we multiply the top and the bottom by just the 4th root of 5, well, that's not going to get rid of the radical in the bottom. See what I mean? But if we combine these two, now we've got 5 to the 4th, and we're taking the 4th root. So now it's going to cancel, and we get 5 in the bottom. That's why it is not good enough just to multiply the top and the bottom by the 4th root of 5, because it's not enough to get rid of the radical. Okay? So make sure you understand that. The goal is to get rid of the radical in the bottom. And so we need something to the 4th power to do it. And so whatever we need to multiply the bottom by to get rid of that radical, then we're going to multiply the top and the bottom by that factor. Okay? And then we end up with this, and we're done. Okay. So let's look at this. So let's simplify these expressions here. So here, we've got these two expressions by 4th roots. Okay, so the first thing we're going to do is simplify the radical by putting it all under the same radical. And so now we're going to simplify this expression by canceling using our properties that we've already gone over. So this simplifies to this. And then we're going to split it back up into different roots again. And so now, since we've already simplified the expression, well, now we're going to rationalize the denominator. And so now, in this case here, we remember, because it's a variable, we can't just simplify this willy-nilly. Okay, so we're going to have to rationalize the denominator to get rid of it. Okay, we can't just write this as x to the 1/2 power. Okay, so we're going to rationalize the top and the bottom. So in this case here, we're going to multiply the top and the bottom by this expression here. And so we're going to end up getting x, and then this here, we're going to combine these, and we get the 4th root of x squared times y, and this is the final answer. Okay. And then for part B, again, now here we have a subtraction. Now, what we're going to end up doing here is we're going to first separate these into the quotients, just like this. So we're going to use the quotient property, the quotient rule, to separate these. Okay, and then what we're going to do is, because these are odd roots, okay, we can just simplify these by canceling these out. So it'd be 6 divided by 3, which gives us 2. This is going to be 9 divided by 3, which gives us 3. And the reason why we're able to do that is because we're dealing with odd roots. So we don't have to worry about the issue that we were talking about earlier with even roots. So now, here, these can stay the same. And in this case here, we don't have any radicals in the denominator to worry about. So all we have to do is get a common denominator. So how do we get a common denominator? Well, here we have to multiply the top and the bottom by x to get x cubed. And now we can combine these as a common denominator, and we're done. And that's it. So sometimes you do not have to worry about rationalizing the denominator. So you just got to practice so that you know when to use it and when not to. Okay. So notice here, this equals -3, a rational number. Okay. This suggests a way to rationalize a denominator that has a binomial in which one or both terms has a square root in it. Okay, so these expressions are called conjugates. So now we're going to show you how, if you have something that has a binomial where it involves a radical as one of the terms or both of the terms, we're going to show you how to rationalize the denominator using conjugate pairs. Okay, so if we look at this example here, we notice that we have a radical in the denominator, but it's part of a binomial. So we can't multiply the top and the bottom by the square root of 2 like we did before, because it's a binomial, and it's not going to get rid of the radical in the denominator by just multiplying by the square root of 2. So in this case, we're going to use the conjugate of this binomial, which is 1 plus the square root of 2. And that's what we're going to use to help us. So we're going to multiply the top and the bottom by 1 plus the square root of 2. And so if you look at that, what happens is this is going to help us get rid of the radical, because the middle term is going to end up disappearing, and the square root of 2 times the square root of 2 is just going to give us 2. So we end up with 1 minus 2 because of this difference of squares. And so we end up with what? 1 minus 2, which is -1. And we end up with this. And so we can end up splitting this up into two fractions, and we get -1 minus the square root of 2, and we're done. Okay, so now this is the end of section 7, so R7. And so again, this is the end of the review, so make sure that you're practicing these exercise problems. Make sure you're practicing and going over these examples, and making sure that you can do these on your own. And if you get stuck, or if you get stuck on any of the exercises or the examples, make sure you reach out to me via email, or work these out, and when you get somewhere, bring those to class, and we can work out those places where you're getting stuck at. Because in in class is where you're going to get the practice and where you're going to apply what you're learning. And all of these review things that we're doing are going to come up over and over and over again throughout the whole semester. So you must learn them now. It will make the rest of the semester easier when you get to these properties and concepts. Because they're going to, again, like I said, they're going to come up over and over again, and I'm not going to rehash these. I'm going to assume that you know these. Okay? So again, we're spending the first week and a half reviewing these so that you can get used to these now, because even though you're not being graded on these as far as the exams, you will be graded on these in the weekly quizzes. Okay? And that's really it. But again, so these are going to be part of what I'm assuming you already know. Okay? So again, practice, ask questions, and I'll see you next time.